Hi, welcome back. Last class we discussed translational partition function. Today in this class we are discussing rotational partition function. Rotational partition. That is in this case we are considering the rotational motion of the molecule and the rotational energy. We are substituting the value of rotation in our molecular partition function. Equation of molecular partition function. You know, Q rotation, which is equal to sigma Gi e raised to minus E rotation by A. Here we are considering the rotational motion, so rotational energy is substituted in our partition function equation, and we get rotational partition function. Okay. Then rotational energy of a molecule, which is equal to J into J plus 1 h square by 8 pi square I, where J is rotational quantum number having value J is equal to 0, 1, 2, etc. Then I is moment of inertia. We know H, Planck's constant, doesn't matter. So this is an equation for rotational energy of a molecule. We are substituting this value in this equation. We get Q rotation is equal to sigma Gi e raised to minus J into J plus 1 h square by 8 pi square I k. That's the equation obtained. But from quantum mechanics, we know the degeneracy of a rotational energy level. The degeneracy of rotational energy level is 2J plus 1. That is what degeneracy. That is Gi is equal to statistical weight factor equal to 2J plus 1. We are substituting this value here, so we get Q rotation is equal to sigma 2J plus 1 into e raised to minus J into J plus 1 divided by h square by 8 pi square I k. Then, to simplify the equation, put h square by 8 pi square I k t. That is h square by 8 pi square I k t is equal to A. Now the equation becomes Q rotation is equal to sigma 2J plus 1 e raised to minus J into J plus 1 into A, where A is equal to h square by 8 pi square I k t. Just for simplification. And as usual in the case of a translational energy level, rotational energy levels are also very close. That is, spacing between the rotational sublevels are very small. So we have to replace this summation by integration. That is, Q rotation is equal to integral J0 to infinity 2J plus 1 e raised to minus J into J plus 1 A dj. That's our equation. So J is equal to 0 to infinity. Then again, to solve this equation, we are making a substitution. That is, suppose x equal to j into j plus 1. X equal to j into j plus 1. That is, which is equal to j square plus j. J square, j into j, j square, j. Suppose x is equal to j into j plus 1. That is j square plus j. On differentiation, dx, we get what? 2j plus 1. 2j plus 1 2j plus 1. 2j plus 1 dj will get. 2j plus 1 dj. So we are replacing 2j plus 1 dj by dx and j into j plus 1 by x. We get the equation as q equal to, that is q rotational is equal to integral j is equal to, or now it is equal to x is equal to 0 to infinity 2j plus 1 into dj dx. J into j plus 1 is equal to x. So e raised to minus x dx, which is nothing but 1 by x. Or here you can say this, sorry, there is an a here. E raised to minus ax dx, which is equal to 1 by a. E raised to minus ax dx, the integral of standard value of that integral e raised to minus ax is 1 by a. So q rotational equal to, that is q rotation is equal to, we know what is a, that is h square by 8 pi square I kt. So 1 by a, that is 8 pi square I kt by h square. That is our equation for rotational partition function. But here this value, that is h square by 8 pi square I k. That's related to thermal energy, and we can put it as theta rotational. That is the characteristic rotational temperature, or characteristic temperature for rotational motion. That is theta rotational. So we can replace this equation as, or rearrange the equation as rotation equal to this as 1 by theta. So theta divided by, sorry, t divided by theta rotation. That's our equation. Or we can say rotation is equal to t divided by q rotation. Characteristic temperature is equal to temperature divided by rotational partition function. Again, moving back to our equation, that is q rotation is equal to 8 pi square I kt by h square. This equation can be used for calculating the degrees of freedom. And we know same configuration, we will get same configuration of a molecule after a rotation by 2 pi radians. When the molecule rotates by 2 pi radians, we get the same appearance, same configuration. Suppose the molecule has some elements of symmetry, then same appearance will be obtained after rotation of 2 pi by sigma, where sigma is symmetry number. Sigma is symmetry number. So if the molecule has elements of symmetry, then we get the same configuration after rotation of 2 pi by sigma radians. So we have to consider this sigma, that is symmetry number also. This symmetry number ensures the avoidance of the repetition of same configuration. Suppose there are two symmetry elements, that is C2 axis for example. We get same appearance, same configuration after rotation of pi radians. If we are not putting the value of sigma here, we don't get a pi value. That is, By 2 pi rotation, we get same configuration 2 times. So repetition of configuration. So to avoid that, we have to include sigma, that is symmetry number, also in our equation. So our equation become Q rotation is equal to 8 pi square I k t divided by sigma h square. So final equation. And for homonuclear diatomic molecule, sigma is equal to 2. Sigma is equal to homoatomic diatomic molecule such as H2, N2, O2. Such molecules. For such molecules, so the value of sigma is 2. And heteronuclear diatomic molecules such as carbon monoxide, nitric oxide, HCl, etc. Sigma is equal to 1. And substituting this value, we can calculate the rotational partition function of the corresponding molecule. So let's up to rotational partition function and its equation. The next it is vibrational partition function. The same approach for the derivation of vibrational partition function, that is Q vibration, which is equal to sigma Ga e raised to minus E vibrational divided by kT. And from quantum mechanics, we know E vibrational is equal to V plus half h nu, or we can write it as n plus half h nu, whatever it may be. Where nu is vibration frequency and can be given as C omega. So we are substituting the value of vibrational energy in this equation. We get Q vibration, which is equal to sigma Gi e raised to minus V plus half h nu divided by kT. That's our equation for vibrational partition function of a molecule. But as we know, vibration sublevels, vibrational energy levels are equally spaced. That is, each levels are at a distance of h nu. At a distance of h nu. That is, they are equally spaced. So we can take degeneracy as 1. So the equation becomes Q vibrational, which is equal to sigma Gi e raised to minus, sorry, there is no G, e raised to minus V plus 1 by 2 h nu by k. Again, as we told, the spacing is equal and they are not close, very close to each other. They are just like that of translation or rotational energy levels, they are not close to each other. So we cannot replace summation by integration. We are doing summation by substituting the values of V, where V is the vibrational quantum number. Vibrational quantum number. And the value is 0, 1, 2, etc. By substituting values of vibrational quantum number, we are doing summation, because we cannot replace summation by integration because the spacings are not close enough. That is, the distance between the other energy levels are not small. They are large enough. That is, spacing is h nu. So we are doing summation. So we get Q vibration as e raised to minus h nu by 2 kT plus e raised to minus, if it is 1 plus 1 by 2, 3 by 2, that is 3 h nu by 2 kT plus e raised to minus 5 h nu by 2 kT, 5 by 2 h nu by kT, so and so and so. And taking out e raised to minus h nu by 2 kT outside, that is e raised to minus h nu by 2 kT out. This become 1 plus this become e raised to minus h nu plus e raised to minus 2h nu plus e raised to minus 3h nu plus so on and so on. As a equation. Okay. Now this series, which is equal to 1 by e raised to minus x plus e raised to minus 2x plus e raised to minus 3x plus so and so, which is equal to 1 by 1 minus e raised to minus x. This expansion is equal to 1 by 1 minus e raised to minus x. That is, which is equivalent to 1 by 1 minus e raised to minus h nu. So there is a mistake everywhere. There is kT. That is h nu by kT is equal to h nu by kT. So we can replace that in our vibration partition function equation, which is equal to e raised to minus h nu by 2 kT into 1 by 1 minus e raised to minus h nu by kT. That is e raised to minus h nu divided by 2 kT divided by 1 minus e raised to h nu by kT. But minus h nu by 2 kT is very small. The value of minus h nu by 2 kT is very small. So Q vibration, which is equal to 1 divided by 1 minus e raised to minus h nu by kT. We can write like that. Or we can replace this h nu by k, that is h nu by k, as theta vibrational, that is characteristic temperature for vibrational motion or characteristic vibration temperature, and we can replace, substitute the value of theta here. We get e raised to minus 5 vibration by 2 T divided by 1 minus e raised to minus 5 vibration by T. That's the equation obtained after substituting the value of characteristic vibration temperature. Okay. Well, two cases arises at very high with very low temperature. At very low temperature, phi vibration divided by T is very much greater than 1. So the value of minus theta vibration by T is negligible compared to 1. The negative of which is negligible. So the equation become Q rotational is equal to e raised to minus 5 vibration by 2T at low temperature. At very high temperature, vibration by T is very less than 1. Very less than 1. So the negative value is very high, so 1 is negligible. Now the equation becomes Q vibrational is equal to e raised to minus theta vibrational by 2t divided by e raised to minus theta vibrational by t. That's our equation for vibrational partition function. Again we can expand this equation. But this is our it is enough for our vibrational partition function. Okay, thanks for listening.